Pre-Cal students, we're just going to take a few minutes to talk about foci, which we mentioned yesterday and today in class. I just wanted to make sure that you guys heard it all one more time. So in a hyperbola, we have vertices and a center, so that's a vertex. Why don't I use that? Okay. So that's a vertex. That's a vertex, and you got the center. Same thing with an ellipse. In addition to a center point, we have the endpoints of the axes, which are also called vertices. So sometimes, so we have 4 of those actually, but these are the ones we care about for what we're going to be talking about. The vertices on what's called the major axis, right? You see how this axis here is longer. Okay, so here's what we need to discuss are the foci. And foci are points, each one is a focus, and together they're foci. So somewhere in here on this major axis, I'll have a point, and in the same place on the other side, I'll have a point, and those will be the foci. And I'm kind of guessing where they are for now. But the idea of the foci in an ellipse is that any point on the ellipse, if I measure that distance and that distance, so let me name these. We'll call it F1 and F2, and we'll say that this is a particular x and y. So here's what's going to be true. What will be true is that the distance from F1 to x, you know what? No. I'm making this complicated. Instead of x and y, let's call it p. All right. And then we can use more traditional, because I was getting off track there. We'll say pf1. Bam. There. See? That's how I'm going to represent the distance. I'll even put measure of line segment from p to f1 plus measure of line segment from p to f2. These, this, and this, these are adding up to a particular constant. So we'll say that adds up to c for a constant. I just picked a letter. But the point is that c is always the same. So that if I go to, say, here, and I have, I measure that distance, and I add these together, I'm still going to get c. Or if I measure that distance and that distance and add those together, it's still going to equal c. Or anywhere, right? I could go right there. Okay, so you get the idea. This is the definition. This is one of the ways to really define an ellipse. It's the set of points at which, if you measure the distances to the two foci from that point, you'd have a sum that is always the same at any point on the ellipse. Now the way that, we're going to have to backtrack a little bit here, so clean this up. So the way that the thing that makes the vertex similar to that is that we have foci here as well. We're going to have a focus somewhere here, and same on the other side. And now with the hyperbola, any point on the hyperbola, if we measure the distance from the foci to that point, the difference is going to be constant. So now, if we take this segment minus that segment, we'll always get the same thing, no matter where we are. We could be here. Whoops, won't let me do that. We could be here. We could be out here. Like that. And we could even be really far down the road in any one of these 4 directions. The hyperbola extends without bound in all 4 directions, and even if I go, a million miles away, I'll still have 2 distances to the 2 foci that subtract to give me the same difference that I would get by subtracting this and this. Okay, so that's what foci are, and I'll name these here also F1 and F2. So what can they do for us? Well, let's say I told you where the foci actually were for this one. So let me just pause for a second. Okay, so we got center, vertex, vertex, focus, focus. Let's say I told you that the distance from the focus down to the center. Let me do it with like this. From the focus to the center, let's say I told you that this distance was the square root of 41. Okay, I'm trying to make this example work out so that it's true to life for this actual hyperbola. So let's say this is a square root of 41. This distance we call c. Okay, so c is the distance from the focus to the center, and that is true here on the hyperbola, and it's also true on any ellipse. From the focus to the center right here, we're going to call that c when we get to that. Okay, but for now we're here and we have this. Okay, so here's the relationship that we can count on. It is the Pythagorean theorem. Okay, now without going into the geometry of how this connects to you know, triangles and all of that, let's look at how we would traditionally make our parametric equations. X equals y equals. Right, so we said that this, you can tell when it's opening up and down, that x is going to be a tangent function of t, and y is going to be a secant function of t. Okay, and then we deal with our h and k, and here we can see our center is at -1, 2. So we get our h and k right off the bat. And then we said that one of these is going to be the distance from the center to a vertex, and we see that that distance is 4. One of these is going to be 4, and this is a vertical distance, so we put it here with the y. This is a vertical scaling. So this is the one where we had such a pain trying to determine what it was, or I mean, it wasn't that big of a deal, but you know, it was a few steps. And we can make it shorter. We can say, if we know the foci, see, and I said before, you got to have extra information, right? So if you didn't know the foci, you'd have to do the same thing we've been doing. But if you know the foci, if you know the location, and you then know the distance from a focus to the center, which is what I'm giving you here, then you can use this, in the sense that we have 4 standing in as one of these, and we have the square root of 41 standing in as c. So 4 squared is 16. Then we can say b squared, which we'll say it's that. And some people are strict and say this is a and this is b. Well, whatever. I don't care. I think it's kind of arbitrary which is a and which is b. And so c squared would be the square root of 41 squared, so that's 41. All right. So you take away 16, and you have b squared is 25, and b is 5. And so now you know what that is. So based on the distance from vertex to center and the distance from focus to center, right? If you know both of those, you can get this mystery coefficient right away with the Pythagorean theorem. Okay, now let's look at a problem involving the ellipse here. Let's say we didn't know where the foci were, which we don't. We don't really know, I guessed. So we don't actually know where the foci are yet, but we know where these vertices are, of course, and we know where the center is. Okay, and we wanted to, let's say we want to determine the foci. Okay, so in this case, once again, c, just as before, c is the distance from the focus to the center. That's still true, right? And this time the relationship is a squared minus b squared equals c squared. A and b, as you know, are kind of like radiuses or radii. It's like it's half the length of an axis is going to be a or b. And what we've been doing is just saying in the parametric equations, whatever the horizontal dimension is, that's what we stick on x. So in this case it'd be 4. And whatever the vertical dimension is, and it's 4 because that's half of the length. It's kind of like a radius. And then the vertical dimension, what is this, 8? Right. We put that on the sine function in the y equation. And we'll throw in, for free, the h and k. Okay, so the point, okay, so we were getting to the foci. So how do we determine where the foci are? Well, one of these we can say is A and one of these is B. And you know what? Like I said before, I'm not interested in keeping arbitrary labels necessarily consistent. I want this to be a little bit more intuitive. In other words, whatever this distance from the focus to the center is, if we square it, which is what we're doing here, that's going to be positive. So clearly we need a larger square minus a smaller square to make this positive result. So if I do 4 squared minus 8 squared, that's going to be negative. So that means that I'm thinking of this as my A. So I'm going to have 8 squared minus 4 squared equals C squared. So 64 minus 16. What is that? 64 minus 16. All right, well, I think it's 48, but I'm doing a lot simultaneously here, so I can't trust myself. Okay, so 48. So you take the square root of 48 and go ahead and simplify that. So if I then take out 4, or I can take out 16, of course, and I have the square root of 16 times the square root of 3, and so that's 4 root 3. So that's going to be approximately, what, 6.8 or some such thing. But I'm not going to even use the decimal. Actually, no, I want to know the decimal because I want to plot this thing. So 4 root 3. Let's see exactly what it is. Okay, 4 times the square root of 3. Okay, 6.9. All right. So approximately 6.9. Okay, so I'm going to show where that is. So from the center, C is 6.9, takes me to here. So I thought the vertex, or at least I randomly guessed the vertex was here. It's actually pretty far out from the center. Okay, and of course, same distance to go on the other side of the center. So we can call that our F1 and our F2.